We are going to see the matrix representation of the Crank-Nicholson method for the Black-Scholes equation. So this is the finite difference representation that we derived for the Crank-Nicholson method. As you can see here, it's a function of some capital A, B, C functions that these are somehow related to the small b, a, b, c functions arising in the Black-Scholes equations. Remember that a was the 1 over 2 sigma square s square, b was r times s, and c is minus r. So these are the functions arising in the Black-Scholes equation, and this is big capital A, B, C functions, which are these ones. Remember that they are slightly different from the ones that we defined in the fully implicit method, and they are just defined this way in order to look this finite difference representation nicer, so in order to make it easier to manipulate. But what we have to keep in mind that these A, B, C functions are the ones that we have defined here. So this was the finite difference representation, and remember that this n is going from 1 to ns minus 1, and the two missing equations, they were taking them from the boundary conditions. And in order to manipulate and implement that Crank-Nicholson method, we know, as we already, the experience, considering experience we already have, and the knowledge we already have from the diffusion equation, it's much easier to manipulate and work with the matrix representation. So here we're going to consider the matrix representation for this finite difference representation. And it's actually, we can follow actually the same strategy that we followed in the fully implicit method. The only main difference here is that here we do have an expression, so we have a matrix both here on the left, where in this case the left, remember, everything depends on j plus 1, and you have another matrix here on the right, where the right, everything depends on j here. So the matrix representation is given by all this expression here. So here we have, this is the matrix we have here on the left. It's a column here, and this is the matrix we do have here on the right. Okay, so we have two matrices. And if you remember, okay, that two matrices, they are non-square matrices. So now it's important, we need to manipulate them in order to get our aim. And remember that our aim is always to clear and have an expression that allows us to get the values of the v functions evaluated at time j plus 1 as a function of the values of the options, in this case, the previous time step. So this is the matrix representation. So we now have two matrices. In the full implicit method, we just have this matrix here on the left. So we're also manipulating that matrix on the left. Here we have two matrices. So we have to manipulate now both sides actually in the same way as we did for the full implicit method. That's why here we're not going to consider uncertainty or analysis and consider how to implement here the boundary conditions in this case, because actually the steps and the strategy that we have to follow is actually the same one as we derived for the, as we explained in the fully implicit method case. The thing is that we have to do that, the same thing here, both on the left-hand side and on the right-hand side. So actually, as we are saying, then now here we have matrices which has ns minus 1 and ns minus 1 rows and ns plus 1 columns, which is a representation of these ns minus 1 equations, but we know that we do have ns plus 1 unknowns. The two equations that we're missing again are coming from the boundary conditions, and using these conditions we are going to convert, as we know, this system of equations into a system of equations involving the square matrices. So the aim again is to transform the previous matrix representation in the following one. So we have here on the left, we have, this is the double B square matrix evaluated at time j plus 1. This is a column vector of just ns minus 1 elements of this v vector evaluated at time j plus 1. Then we have another column vector, which actually would implement somehow, in case it exists, the boundary conditions. And then the same thing on the right-hand side, where we have another square matrix and another column we're calling R. And in this case, everything depends on J. And after having that, that's very easy. Once we have these square matrices, it's very easy from here to clear and have an expression for V evaluated at time j plus 1, everything as a function of known both column vectors and matrices, and also the values of the V vector, but in this case evaluated at the previous time step, at time step j. And all these boundary conditions will be fully incorporated both here in these matrix components or in the column elements of this column vector. But again, here we are not going to give more details on how to implement the boundary conditions in this case, because actually the steps and the strategy that you have to follow is actually the same one as the one we have just derived in the case of the fully implicit method.